The following video contains content that may not be suitable for all ages. The content contains, but not limited to, the following: hypothetical animal endangerment and abuse, zombie cats, mad scientists, vials of poisonous gas, and most importantly, physics. You have been warned. Hello to anyone who is watching this right now. Over the last weekish, I've been asked a lot about Schrodinger's cat and what it means and its implications. And by a lot, I mean I've had 6 conversations within the last 3 days about it. And so I decided, it's spring break, I have my whole suite to myself. What better way to spend my time than to make a physics video? So I might as well get started. Before we can actually talk about Schrodinger's cat, we need to kind of talk about the physics that led up to it. And Schrodinger's cat comes from a time of the 20th century. Now, prior to the 20th century, physics was pretty straightforward. It was all Newtonian physics. You have an object, you know kind of where it's at, you put a force to it, and then you can predict what will happen. I take this dry erase marker pen, I let gravity take control, it's going to fall straight down. Hey, I was right. Newton was right. Fairly straightforward. Now, you get to the 20th century, and that changes. Once we start looking at the very, very small objects like particles like electrons and photons and things like that. And a prime example of this is the double slit experiment, where it was observed that particles, specifically electrons, act like a wave and like a particle, depending on the conditions. And just to show exactly what I mean, what they did was they took an electron emitter and they just fired, electron by electron at a wall. Now, in the first case, like I'm about to show you here, there was just one slit, and when that happened, the electrons acted like electrons do, and they behaved like particles. And the detector observed basically this. The electrons went straight through, and there was a cluster of hits right across from the opening of the hole. Now, that's perfectly normal. That's what they expected them to act like. But once you added a slit like this, so there's 2 holes to go through, you'd expect just on the other end there to be just 2 distinct spots of where they hit. But that wasn't exactly what happened. What happened was it was more of a wave-like effect, and you got an interference pattern. And if I just draw a very basic one right now, something like this happened, where the particle, the electron, went through the wall, and then the detector detected this pattern, which can't be explained if it acted like a particle. So it acted exactly as a classical wave would, and they did this with, one electron at a time, and they observed it. So there's no way electrons could have been interfering with other electrons. They must have been interfering with themselves or acting like a wave. And this wave-particle duality was a big problem during this time. The top physicists of the time had differing views on it. Einstein was not a fan of quantum mechanics at all. He stated that God does not play dice, but as we know now, kind of seems like he does. Quantum mechanics is very probabilistic in nature, and the most common explanation for it is the Copenhagen interpretation, which was thought up by Niels Bohr and Warning Heisenberg. And basically what it says is that a physical system, before it's observed, is very probabilistic in nature. So say, this side of my whiteboard is the physical system, and you obviously can't see what's on there. Now I can tell you I'm going to write a number from 0 to 10 on there. one single number, 0 to 10. Now, when you're not looking, it is every number possible that I could write there. It's all of them in a weird kind of cluster of probability. But once I turn it, once you observe it, it collapses into a single system. In this case, 7. But when you weren't looking, it was every single possible number. Now, that collapse into the 7 in this case is called a wave function collapse. And this is what Schrodinger was talking about when he talked about his famous cat. In the beginning, in the warning of this video, it said this may contain mad scientists. And that's true. Schrodinger was a mad scientist. But he didn't actually put a cat in a box and see if it was alive or dead. He was mad at the Copenhagen interpretation of quantum mechanics. He didn't agree with it. He didn't like the result that you got, the implications. So he showed how ridiculous it is. And what he did was he said, say you take, a box, and in that box you put a cat. So you have a cat in a box right now. And then also in that box you add a vial of deadly gas. It's closed. You can't get out unless it's broken. Not too much of a problem, except Schrodinger also added a piece of radioactive element and a Geiger counter and a hammer. Now, he put the cat in the box for an hour, and in that hour, there's a 50-50 chance that this element will decay and release an electron. If it decays and if it releases the electron, it will trigger the Geiger counter, and the Geiger counter will trigger the hammer will smash the glass, and the cat will die. Now, you can't observe it. The only way you can observe it is by opening the box. Now, until you open the box, the particle that was going to decay was in a superposition of being both decayed and not decayed, which in that case the cat would be both in a state of being alive and being dead. It's not a zombie cat, it's just in a superposition. Now, Schrodinger said, you open the box and then you see if it's alive or dead, and, the wave function collapsed. But the cat was always in the box, and the cat would know if it was always alive or if it was always dead. And Schrodinger was just showing how ridiculous the Copenhagen interpretation of quantum physics was. The thing is, that's the best explanation we have right now for quantum mechanics. And it is one of the most widely taught, and it's still one of the most accurate, for lack of a better word. There are some other things. Take, for example, the many worlds interpretation of quantum mechanics, which would be that it does decay and it also does not decay, and two different branches of reality, split, kind of like a Back to the Future type thing. And there's a reality where the cat's alive, and there's a reality where the cat is dead. Now, I hope that explanation was thorough enough, and I didn't mess up at all. I don't think I did. But if you guys have any questions about it or would like me to actually talk about something else in the future, let me know. I'm always down to explain and practice my teaching skills. So I hope that helps explain it, and if not, message me and I will do my best to answer any questions you have. So thanks for watching, and hopefully you guys leave me alone about Schrodinger's cat from now on, because it was starting to get annoying. So, yep, that's it.